In this video, we are going to discuss Chapter 7. Chapter 7 is all about continuous probability distribution. In the Chapter 7 of continuous probability distribution, our main focus will be normal distribution, continuous probability distribution. Last chapter, Chapter 6, we looked at discrete probability distribution. Binomial probability distribution was an example of discrete probability distribution because in that case my random variable could only take discrete values. My random variable could take the values like 1, 2, 3, 5, 6, 10, 0. It could not take measurable values, it could take countable values. But for continuous probability distribution, our focus is going to be our random variable would be continuous random variable. Continuous random variable means it can take measurable values, it can take infinite values. So anything between 0 and 10 and all the values in between, depending on how precise you want to be. So foot length is an example of a continuous random variable. Okay. So in this chapter, our main focus we'll start with uniform distribution, and then we'll look at properties of normal distribution, and then we'll also look at standard normal distribution and just normal distribution. There's a small difference in the standard normal and normal distribution. Let us start with uniform distribution. Uniform distribution is a continuous random variable has a uniform distribution if its values are spread evenly over the range of possibilities. The graph of a uniform distribution results in a rectangular shape. So here's an example of how a uniform distribution looks like. It's a continuous variable, for example, time. Time would be a continuous random variable, and we can express it using the uniform distribution. There's two main requirements for uniform density curve or uniform distribution. First one, the area under the curve is 1. Second, every point on the curve has a vertical height that is 0 or greater. Curve cannot fall below x-axis. Because the total area under the curve is 1, therefore there is a correspondence between area and probability. Okay, so we just said that the area under the curve is 1. Let's see, if I start at point A and end at point B, what is going to be this purple marked length? That would be B minus A. And we want the area to be equal to 1. How do we find area of a rectangle? Area of a rectangle is always equal to length times width. And in this case, we want the area to be 1, and we know the length is B minus A. The width or the height has to be 1 over B minus A. So that's where this comes from. The height has to be B minus A. The purple mark line has to be 1 over B minus A. Only then the area can equal 1. Here's our first example for uniform distribution. Suppose you have a friend who comes late to the class every day. The time he is late, so I'm told the time he's late is uniformly distributed. So that's what tells me that I'm dealing with the uniform distribution problem. It could also say that the time is evenly spread or evenly distributed. That would also mean uniform distribution. The time he's late is uniformly distributed over the interval from 0 to 30 minutes. So part A, what is the probability that your friend is 10 or fewer minutes late? Okay, 10 or fewer minutes late. So let's go ahead and first of all draw the probability density curve here. So in our probability density curve, we have the time on the bottom and probability on the side, okay? So I'm going to call the time as x and probability of x here. And it tells me that the time he comes late is uniformly distributed over the 30 minutes, 0 to 30 minutes. Okay, for part A, we're looking for find the probability that your friend is 10 or fewer minutes late. So this is P of X. I did not need the eraser. Less than equal to 10. So let's go ahead and look at less than equal to 10. So if this is my origin, if this is 30, what is the height going to be? Remember, the area always has to equal 1. If the area is equal to 1, then the green height has to equal 1 over 30. Only then our area would be equal to 1. The green height has to equal 1 over 30. Let's try to answer the first question. What's the probability that he's 10 or fewer minutes later? So Instead of drawing a new distribution, I'm just gonna make changes to the one I already have. 10 or fewer minutes later, so that would be this one, and I'm trying to find probability of this region. Probability and area correspond to each other. So in statistics, whenever you hear me talking about the area, it is same thing as probability. Whenever you hear me talking about the probability, it's same thing as area. Okay, there's a correspondence between the area under the curve and the probability. Okay, so area, so now I'm looking for this pink shaded area. What is the area for this rectangle? Well, the new length is 10 and the height is still 1 over 30, so probability turns out to be 1/3. The probability that your friend will be 10 or fewer minutes late is 1/3, and we can change it to the decimal if we really want, or we can always express probability in terms of fraction or decimal, both are fine. So 33.33% chances, if you want to change it to a percentage or decimal, 33.33% chances that your friend will be always interpret your answers. Okay, your friend will be 10 or fewer minutes late. 10 or fewer minutes late. All right, for part B, probability of x lying between 20 and 25. Now for the next problem, again, I'm going to draw my curve. I'm not going to mess with the other one. I'm going to draw a new curve here. So still 30, and this is 1 over 30. Now we're trying to figure out what's the probability that he arrives between 20 and 25 minutes. So I'm just going to, by estimate, draw, there's 20, there's 25. We want to find area of this rectangle now. What is the length of this rectangle? Between 20 to 25, the length is 5 and the height is still 1 over 30. That turns out to be 1/6. Again, we can change it to decimal if we want and then interpret your answer, or we can leave it as a fraction and still interpret your answer that there's 1/6 chances that your friend will be arriving between 20 to 25 minutes. What is the probability that your friend arrives exactly 15 minutes after the class starts? Whenever you're talking about the word exactly in a continuous probability distribution, your answer is going to be impossible, 0 probability. So probability would be 0 in this case. Probability that your friend arrives exactly at 15 minutes, probability that your friend arrives exactly at 15 minutes is going to be 0. Why? Think about drawing your rectangle. So it goes up to 30, and now we have, goes up to 30, exactly 15 minutes. Think about exactly 15 minutes. 15 minutes is here, but we are talking about a continuous variable and we don't have any width of the rectangle. We do have the height is 1 over 30. The width of the rectangle is 0. So width of the rectangle is 0 because we are not looking between 14 and 16. We're not looking between 14.9 and 15.1. We're looking at exactly 15. That gives me the width of the rectangle is 0. The height is 1 over 30. And that turns out to be 0 probability. 0% chances that your friend will be exactly 15 minutes late. Okay, could be 15.01, 15.02, because it's a continuous distribution. So chances of something exactly are going to be 0. For me to be able to guess the money in your pocket and say, oh, well, you have exactly $205 in your pocket, probability of that happening is 0, unless I already knew it. For me to be able to say, well, you have under $200 in your pocket or over $200 in your pocket, higher chances of that being true. Okay, next example. A car company can produce one car in 14 to 16 hours. These times are uniformly distributed. Okay, so these times are uniformly distributed. For a car to be built, it takes 14 to 16 hours. Okay, find the probability that a randomly selected time measurement hour is greater than 15.5. So we're looking for the probability of a car being made in greater than 15.5 hours. So let's go ahead and look at 15.5, and 16 is here. We already know because we are given between 14 and 16, this distance will be 2. In order for area to be 1, the height has to be 1/2. Okay, so this turns out to be between 15.5 and 6. My width of this shaded rectangle is 0.5 and the height is 1/2, so that's going to be 1/4. So 25% is the area. And we can interpret and say the probability that a randomly selected car took more than 15.5 hours to make is 25% or 0.25. Next problem, assume that the weight loss for the first month of a diet program varies between 6 pounds and 12 pounds. So weight loss varies between 6 pounds and 12 pounds and is spread evenly over the range of possibilities, weight loss values. Okay, find the probability that a randomly selected participant in the program loses more than 10 pounds in the first month of program. Let's go ahead and draw our curve first. We are being told that it is uniform distribution. It's evenly spread. So the weight loss is spread between 6 pounds and 12 pounds. 6 pounds and 12 pounds. Without even thinking about the next step, I already know that this pink length that I'm marking pink right now, that is equal to 6. So that means the green height has to be 1/6. Only then the area will be equal to 1. The green height is 1/6. Only then the area will be equal to 1. Find the probability that a randomly selected participant in the program loses more than 10 pounds. So we're looking for the probability of somebody losing more than 10 pounds. Let's go ahead and draw our rectangle for more than 10 pounds. I'm just estimating 10 pounds is here. So we're basically interested in finding out the probability of randomly selecting somebody who loses more than 10 pounds. And that would be the area of the shaded rectangle. For the shaded rectangle, my length of the rectangle is 2. My width is 1/6, and altogether turns out to be 1/3. So probability that a randomly selected participant loses more than 10 pounds is again 33.33% in this case. Okay, that finishes the uniform distribution. Now we're going to look at the normal probability distribution. Okay, the normal probability distribution, properties of normal distribution. So here we are, properties of normal distribution, attributes of normal distribution, bell-shaped, symmetric about mean. The normal distribution is bell-shaped distribution. It is symmetric about the mean. That means half of your area is to the left of the mean and half of your area is to the right of the mean. And it's a continuous curve. This is a continuous curve. It never touches the x-axis. This curve is never going to touch the x-axis. It comes really, really close to the x-axis, but it is never going to touch the x-axis. Comes really, really close to the x-axis, but it never really touches the x-axis. Total area under the curve is 1. Isn't that amazing? You have infinite area, but it adds up to 1. So all this area under the curve is equal to 1. Area and probability are equivalent in statistics. So whenever we talk about the area, just know we're talking about the probability, or whenever we're talking about probability, translate that it's talking about the area. Approximately 68% lies within 1 standard deviation of mean, 95% of the lies within 2 standard deviations of mean, and 99.7% lies within 3 standard deviations of mean. This is the empirical rule mentioned earlier. We talked about the empirical rule. We're going to see the picture in a minute. Now, data values represented by x as a mean, mu, and the standard deviation sigma. This is probability density function. If you took calculus 2, you should have seen this function, probability density function. But if you have not taken calculus, then you have not seen this function. And don't worry about memorizing it. You don't need to memorize this. But this is just the function of x, mu, and sigma. It's called probability density function. Okay, empirical rule here is the picture. We talked about empirical rule in chapter 3. It only applies to symmetric normal curve, symmetric, bell-shaped, or normal, all mean the same thing. And empirical rule says that 68% of the data lies within one standard deviation of the mean. Our mean is in the middle, exactly in the middle. And then I'm moving one standard deviation away, two standard deviations away. I'm doing both, moving above and below. Mean, one standard deviation above the mean, two above the mean, and three above the mean, and same thing, one below the mean, two below the mean, and three below the mean. Okay, let's look at the standard normal distribution. So there's slight difference between the standard normal distribution and normal distribution. In a standard normal distribution, I just showed you in the empirical rule without calling it standard normal distribution, the mean is 0. Okay, you are expressing your data values in terms of the z-scores. The data values are expressed in terms of the z-score. Formula to calculate the z-score was z equals x minus mu over sigma. X minus mu over sigma, that is the formula to calculate the z-score. So in a standard normal distribution, data values are converted into mean, into z-scores. Data values are converted into z-scores. And standard normal distribution, the mean is 0. The mean is 0, so that means the data value is 0 as well when the mean is 0. The variance is 1 and standard deviation is also 1. Remember, standard deviation is square root of the variance. The data values are represented by the z-score. So z-score represents the data values. So for a standard normal distribution, z-score and data values are same. For a standard normal distribution, z-score and the data values are same. So remember that z-score and data values are same for standard normal distribution, and that's not true for the normal distribution, which we will look at a little later. And here is the probability density function for a standard normal curve. Again, no need to memorize this function. Okay, normal probabilities, positive and negative z-score tables. So earlier in previous chapter number 3, we saw z-score can be calculated using this formula, x minus mu over sigma, where x is your data value, mu is the mean, sigma is standard deviation. So it's data value minus the mean divided by standard deviation. That's how we calculated the z-score. Now, the z-score can be equal to 0. If your data value is the mean itself, then the z-score will be 0. If your data value is higher than the mean, above your mean, then the z-score will be positive. If the data value is below your mean, z-score will be negative. So z-score, we always round it to 2 decimal places. Some special ones are used with the 3 decimal places as well, but mostly z-scores are rounded to the 2 decimal places. So we break the z-score into 2 parts, the whole number and the tenths are looked up along the left side and the hundredths is looked up across the top. So I'm going to take you to the z-score table now and show you how does a z-score table look. So here is a standard normal distribution table. This is the one that comes with our textbook, okay? And here's a picture of standard normal distribution. This picture is important because this picture is telling me that this table gives you area to the left of a z-score. In some textbooks, they give us area to the right of the z-score, but in this one, it gives us the area to the left of the z-score. Okay, so we're looking at the area to the left of the z-score. All right, so how are we going to read the z-scores? There's the negative z-scores here. All the ones up to this point are negative z-scores. Some textbooks have a different table for negative z-scores and a different table for positive z-scores. And all the ones over here are positive z-scores. And how do you read the z-score? In the middle, all these are the areas. So yellow highlighted are the areas. So all these are the areas, okay? And these yellow highlighted are the areas. So in the middle of the table, in the body of the table, you have the areas given. And the top row and the very first column are your z-scores. So if you want to find out the area to the left of negative 2.95, okay, negative 2.95. You want to find the area to the left of negative 2.95. How do you find that area? Let's take a look. To find the area to the left of negative 2.95. So I'm going to first look up the z-score negative 2.9, which is negative 2.9, highlighter, negative 2.9. And then we have 0.05 here. So wherever these two columns meet, that is the area to the left of negative 2.95. And that looks like that area would be 0.0016. So if my z-score is negative 2.95, I have about 0.16% area to its left, okay? Area to the left. Again, this table gives us area to the left. This table gives us area to the left. Now, what if I want to find out the area to the right of it? Think about where would be negative 2.95. My 0 is exactly in the middle, so let me draw the curve. We already saw the normal curve earlier. So 0 is exactly in the middle. And then I am 1 standard deviation above, 2 above, 3 above, negative 1, negative 2, negative 3. So I'm representing my data values with the z-score in a standard normal curve. And I'm talking with negative 2.95. I'm approximating the negative 2.95 is approximately here. And we were looking for area to the left of it. Area to the left of the negative 2.95 turns out to be 0.0016, almost 0% area, very small amount of area to the left of this. How about if I wanted to find out the area to the right of it? So here we just did area to the left of negative 2.95. How do I find area to the right of negative 2.95? Area to the right of negative 2.95. Area to the right of negative 2.95 is all this area, but I'm not going to bother about, calculating that because I already know the entire area is equal to 1. So if area to the left is 0.0016, then area to the right would be 1 minus 0.0016. That is going to be area to the right, which is going to be, so 1 minus 0.0016, that turns out to be 0.9984. So this is how much area is to the, I combined two steps. 1 minus 0.0016, which is equal to 0.9984, and that's the amount of area I would have to the right of it, okay? That's how we read the z-score. If you have a positive z-score, same process. If you want to find out area for positive z-score, we will look in the positive z-scores. Area to the left of 1.23. Area to the left of 1.23. So let me grab a pink highlighter now. So I'm going to look for 1.2 here, and then I want to also find out 0.03 all the way from the top, and wherever those two meet, that's the area. Looks like 0.8907. So this is how much area I have to the left, 0.8907 to the left of 1.23. Where is 1.23 on your standard normal curve? Think about, you have 0 over here, 1 standard deviation here. 1.23 is approximately here, and that's where it would come out to be, 0.8907. Now what if I want to find out area to the right? Area to the right of 1.23, I would just subtract all the area that it has to the left. 1 minus 0.8907, that turns out to be 0.1093, 0.8907, that's 0.1093. Now that's how we read the z-score table, okay? Most of the problems I will be doing for the homework now, I will be using the tables to show you how the tables work, but you can also save time by using the Casio 991 calculator, and instead of looking at the table every time, you could be doing the problems much faster using the Casio calculator. I'm gonna also post another video showing you how to use a StatCrunch to find these areas. Okay, back to the notes. All right. So if you, again, remember your standard normal curve, how does it look? In your standard normal curve, you have mean in the middle. Your mean, your data values, and the z-scores are same for the standard normal curve. So 0 goes in the middle. And then you are 1 standard deviation above, 2 standard deviations above, and 3 above. Then you're 1 standard deviation below, 2 below, and 3 below. Okay, and beyond that, there's almost 0% of the area. There is very small amount of area to the left of -3 and to the right of +3 standard deviations. Okay, one more thing, I have it somewhere in the notes that you should memorize. The z-scores can be positive or negative, but the area and probability are not. So z-score can be positive or negative, but the area or probability is never negative. Never negative. Area and probability are never negative. But z-scores can be positive or negative. Okay, computing normal probabilities. There are several different situations that can arise when asking you to find normal probabilities, and I highly recommend that you shade your curve, especially in the beginning before you get to the table. Draw and shade your curve. So if you're looking for between 0 and any number, where is the 0 on your standard normal curve? 0 is exactly in the middle. So if you're looking between a 0 and a negative number, then that's the area you're looking for. If you're looking between 0 and a positive number, then that's the area you're looking for. Okay, between 2 positives or 2 negatives. Okay, between 2 positives or 2 negatives, let's think about if you're looking between 2 negatives. So this can be your negative B and this can be your negative C. This is the area you're looking for. Positive z-scores are above your mean. So between 2 positive z-scores, you could be looking at that region. Between a negative and a positive, we will actually tell you what z-score we are talking about. Between a negative z-scores are like here, and positive z-scores are like there. So you're looking for all this area in the middle. Less than a negative or greater than a positive. So let's go ahead and draw that. Let's say this is -A. Less than a negative means you're looking for this area, or greater than a positive. If you recall the addition rule of probability, whenever you see the or, you're going to add these two areas. Add these two areas. You're going to be adding these two areas, okay? Greater than a negative or less than a positive. Okay, greater than a negative or less than a positive. So this is -A, this is +B. Greater is to the right, less is to the left. So you're looking at this much area in the middle here. Let's look at a couple of examples of standard normal distribution, and then we will look at the normal distribution, which is the next section, 7.2. Here's first example. It's worked out in the notes for you. I'm going to go through it quickly, and I'm going to spend more time on the examples that are not worked out so that I can do them with you. Okay. Testing thermometer quality. Suppose that most of the thermometers freeze at 0 degrees Celsius, but some are freezing below or above 0. Assume that the mean is 0 and the standard deviation is 1. Whenever I see this, mean is 0 and the standard deviation is 1, I already know that I'm dealing with the standard normal distribution, okay? I'm dealing with the standard normal distribution whenever the mean is 0 and the standard deviation is 1, because that's a property of standard normal distribution. If one thermometer is randomly selected, find the probability that the thermometer reads less than 1.27 when water freezes, not 0. Okay, less than 1.27. So we're looking for the probability of less than 1.27. First of all, on my curve, I need to figure out where is 1.27. Well, it's a positive z-score and it's going to be above my mean. So approximately that's where 1.27 is. And we're looking for the area to the left of 1.27. Remember, in a standard normal curve, the z-scores and the data values are the same. So if you were to find the z-score for 1.27, because your mean is 0, because your standard deviation is 1, your z-score will turn out to be same as the data value. Okay, we're looking for the area below 1.27. Below is the same thing as to the left of 1.27. Saying below or saying to the left is the same thing. Now let's go ahead and read our table. We want the area to the left of 1.27. I'm going to look in the positive z-scores. So stats table, let me clear this table really quick, clear the page. Okay, to below 1.27. So here we are, 1.2, positive z-scores, 1.2. And then I also want to find out 0.07 above. And wherever they meet, that is going to be my z-score. And I can see, looks like it's 0.8980. Going back to the notes, so 0.8980. How do you interpret this? What does this really mean? Simply means there is about 89%, 89.80% chances that if you randomly select a thermometer, it would be freezing below 1.27. Okay, that probability that the thermometer reads less than 1.27 when the water freezes, there's high chances, about 90% chances of that happening. Here we are finding the indicated probabilities. Probability of z less than 1.645. So we're looking for 1.645 is positive. We're looking for how much area is to the left of 1.645. Again, because my z-score table does not give me 3 decimal places, I can go ahead and just round it to 2 decimal places, and I can look for probability of z less than 1.65. So on my table, 1.65, let's see, where is that? And sometimes the special ones are actually given below on the bottom. 1.65 is here. And we can see it's 0.9505. It's deviating a little bit from what we see in here because I don't have I'm not using 1.645, I'm using 1.65. So I see 0.9505, and there's not a big difference. Still 95% chances. Okay, so 0.9500. This is more accurate because you could be using a calculator or StatCrunch to get these values, and your answer would be more accurate. For z values greater than 3.49, it's important to remember if you have a z-score greater than 3.49, we can assume that this is the area to the left. And for z-score less than negative 3.49, this is the area to the left. Why is it okay to assume? Because we already said that a lot of area, 3.49, within 3 standard deviations, you have 99.7% of the area. So all this area would be almost all of the area, which we're going to say 99.99%. And if we are looking for to the left of negative 3.49, it's almost 0% area to the left of it. Because most of my data values lie within 3 standard deviations. To the left of negative 3 and to the right of positive 3, I almost have 0% area. Okay, finding the z-score from the probability, this one is a little bit more difficult when you're finding the z-score from the probability or from the area, because we will be using the table inversely here. Given the probability of something, find the corresponding z-score. So first of all, we're going to draw the curve, and then we will be looking for the area in the body of the table, okay? We'll be looking for the area in the body of the table, maybe not exact, but we'll be looking for the area in the body of the table. We may not find the exact area in there. We'll go with the one that is closest, okay? Again, remember, z-score can be negative, but the area and probability cannot be negative. Now let's go back to the table. If you want to find out what z-score corresponds to, what is the z-score? So let me draw the curve here. What is the z-score that has 0.9279 area to its left? 0.9279 area to its left. What is the z-score that has 0.9279 area to its left? So I'm going to have to look for this number in the body of the table, 0.9279. Looks like there's 0.9279 here. And how do I find the z-score? Same like we did before. So it's 1.4 and 1.46. So 1.46, I can already tell it's a positive z-score because it's got a lot of area to the left. So 1.46 is a z-score that has 92% area to the left. 1.46 is the z-score that has 92% area to its left. Okay, back to the notes. Another question. Some thermometer sampling form before with mu equals 0 and sigma equals 1. So same thermometer sampling from before that we talked about earlier. The mean is 0, sigma is 1. That means I'm dealing with the standard normal curve where my data values are same as the z-scores. Data values are same as the z-scores. Data values are same as z-scores. Okay, find the temperature corresponding to P95. What does P95 mean? P95 is a 95th percentile. That means the 95% of the area is to the left. 95% area to the left means a lot of area to the left. 95% area to the left means there's a lot of area to the left. Okay, so how do I find the z-score that has 0.95 area to the left? I'm gonna go to the table and find out 0.95. Because I'm only given 0.95, I can always make it 4 decimal places because the area is always in the 4 decimal places given to me in here. Let's look at the right table, not the T table. We're looking at the Z table in this case. So 9,500, let's go ahead and find out where is 9,500. Well, there I see two values, 94.95, 95.05. Now, which one is closer out of these two? Which one is closest to 9,500? Well, they both look exactly same distance apart. So I can estimate and say, well, this is going to be somewhere between 1.64 and somewhere between 1.65. What is between 1.64 and 1.65? How do we find the middle of 1.64 and 1.65? To find the average, we can say the average, because they're in between two values, the middle would be, I can find the average and say the z-score will be between 1.64 plus 1.64 plus 1.65 divided by 2 turns out to be 1.645. So back to our notes, it turns out to be 1.645 is, and that's a typo, should be 0.9500. The area of 0.9500, 95th percentile, corresponds to the z-score of 1.645. When tested at freezing, 95% of the readings will be less than 1.645. And that's the context. It's very important to interpret your answer. What does that number mean that you are saying is your answer? What does it mean in terms of the problem? Find the temperature separating the bottom 2.5% and the top 2.5%. The good thing about this problem is anytime we're talking about bottom 2.5% and the top 2.5%, I don't need to find both because I know normal distribution is symmetric. So that means whatever z-score is corresponding to the bottom 2.5%, the same z-score will be corresponding to the top z-score, top 2.5%, except that those z-scores will be positive or negative. Because my table gives me area to the left, I'm gonna find the negative one first and just make it positive on the other side. Okay, so the area is 2.5%. If I change it to the decimal, 2.5%. If I change it to the decimal, move the decimal 2 places to the left, 0.025. So I need to go look for in the body of the table 0.025. Let's look for 0.025 in the body of the table. 0.025 in the body of the table and find out the corresponding 0.025. Looks like somewhere here I see that. Okay, I see that's 0.00. I don't want 0.00, I want 0.025. 0.0256. Actually, that's not very accurate because look at the next one. There I have the exactly 0.025. So my z-score turns out to be negative 1.96. Negative 1.96 is my z-score. So let's go back to negative 1.96 is the z-score here. So I can just make the z-score positive here because I know that normal distribution is symmetric. So if it's got 0.025 here to the left, the 1.96 z-score will have 0.025 area to the right. Okay, if you want to go the longer route, you can also do this longer route. If we are looking for the one that has 0.025 area to the right, it would have 1 minus 0.025 to the left. So what's 1 minus 0.025? 1 minus 0.025 turns out to be 0.975. We can look for 0.975 in the body of the table and find out where is 0.975, and here we go. 0.975 is right here. So I'm gonna circle it and then back to the highlighter. So it turns out to be 1.96 positive, and I didn't really need to do all the work twice. I could save myself time by just using the symmetry for a normal curve. Okay, critical value. What is a critical value? Critical values are the z-scores that have alpha area to the right. So critical value is usually expressed as z alpha, and it's got alpha area to its right. Z alpha, it's got alpha area to its right. So we're looking for this critical value z 0.9222. In chapter 7, we will not use these critical values a whole lot. We will just learn how to find these. But in chapter 9, we will use these critical values when you're finding out confidence intervals. In this case, alpha is 0.922. So we're looking for z alpha. Alpha is the area to the right, area to the right. The problem is my table does not give me area to the right. It actually gives me area to the left. So I'm going to think about it in terms of area to the left, because this is the z-score that has alpha area to the right. If it's got alpha area to the right, it would have 1 minus alpha area to the left. So this, it would have 1 minus alpha, which is 1 minus 0.9222, to area to the left. So I'm looking for the z-score that has, sorry, I need the eraser. I'm looking for the z-score that has 0.0778 area to its left. So in my z-score table, I'm going to be looking for 0.0778. This is the area. So I'm going to look for it in the body of the table. Anytime you're given a z-score, you're looking in the first column and the first row. But if you're looking for if you're given the area you're looking in the body of the table. So in the body of the table, I'm going to find out 0.0778. 0.0778. I'm going to clear the table really quick because I don't need these written over here. 0.0778. Let's see, where is 0.0? Well, that wasn't too much work. So it's right over here. What is the z-score? Turns out to be negative 1.42. Negative 1.42 is the z-score here. So negative 1.42 is the z-score here. Okay, find the z 0.025. Here's another critical value problem. We're looking for the z-score that has 0.025 area, this much area to its right. If it's got this much area to the right, it would have 0.9750 to the left. Because go ahead and draw 0.025. So 0.025 is the area to the right. It's not the z-score, it's the area to the right. How much area would it have to the left? So all this blue area, because the total area is 1, the blue area would be 1 minus 0.025, which is 0.9750. And that z-score turns out to be 0.9750. Let's look in the body of the table. 0.9750, clean this page, clear this page. 0.9750. Let's see, what does that turn out to be? 0.9750. Don't see it yet. 0.9750. I see 0.97 right here. Okay, so 0.9750 is here. And again, if I highlight 1.96 is what I'm going to get. 1.96. Okay, there we go. 1.96 is what I'm going to get. 1.96. Okay, z is 0.025, area to the right. The critical value will be 1.96. All right, let's see. Always remember to label and sketch and shade the curve. When looking for area or probability, you will be looking at the z-scores, left row and top column intersection. When looking for the data value corresponding z-score, in standard normal distribution, data value and the z-scores are the same. When looking for data value or corresponding z-score, you will be looking in the body of the table and find the corresponding z-scores. Okay, let's go ahead and practice using the z-score table. I'm not going to do every single one of these problems. I'm going to do part A of each and have you do part B and match your answer with me. Okay, for part A, we are looking for cumulative area. When we're talking about cumulative area, we are talking about area to the left, okay? Where is 1.25? 1.25 is here. Area to the left of 1.25. I'm going to go back to my z-score table and find out area to the left of 1.25. 1.25, let's get a highlighter. 1.25. Oh, I think I went too far. 1.25, no, I was right. There we go, 0.8944. So I can say this is going to equal, not a highlighter, 0.8944. 0.8944, is that correct? 0.8944, right. Okay, for the next part B, you're looking for area to the left of negative 2.31. I think negative 2.31 is somewhere here, just my estimate. And this is, if you read the table, it is going to be 0.01044. 0.01044, okay, 0.01044. Now for the second one, we're looking for area to the right. For part A, we want area to the right of 1.36. So first go ahead and draw 1.36. We know 0 is in the middle, and then we have 1 standard deviation. 1.36, and we want area to the right of it. Remember, my table does not give me area to the right, but instead it gives me area to the left. So whatever I get from the table, I have to do 1 minus that number. Let's look at the table for 1.36. 1.36, let me get a different colored highlighter. 1.36 looks like 0.9131. Looks like it's 0.9131, and I have to do 1 minus this number because this is the area to the left, but I want I forgot what it was. It was 0.9131. 0.9131. And 1 minus 0.9131 turns out to be 0.0869. 0.0869. Okay, that is my area to the left. For part B, we want to find out area. This is the area to the right. This was the area to the left. But we were not looking for area to the left. We were looking for area to the right. So we had to subtract from 1. Go ahead and try part B and part C by yourself and come back and match and check your answers with me. This one should be 0.9962 and this one should be 0.0008. Okay, looking for area to the right. Next problem, we're looking for the area between these two z-scores. So let's first of all, for part A, I'm going to go ahead and draw these two z-scores. We have negative 2.55, I believe. Negative 2.55 is somewhere here. And then we have 1.08, I believe it's approximately here if 0 is in the middle, which is my mean. And we want the area in here. Now my table does not give me area in between, but what I can do is we can find area to the left of 1.08 and find area to the left of negative 2.55 and subtract those two areas because they will give me the difference. They will subtract those two areas and they will give me in between areas. Because look at all the area we have to the left of 1.08. The area to the left of 1.08 is all this yellow area. And area to the left of negative 2.55 is all this green area. And if I subtract the total yellow area minus the green area, then I have the leftover area in the middle. Okay, so area to the left of 1.08, go back to the table. 1.08, clear the table. 1.08, I am looking at 1.08, I believe. It's 0.8599. Okay, 0.8599. And so 0.8599. Now I want the area to the left of negative 2.55. Area to the left of negative 2.55. Negative 2.55 is negative 2.55 is here, which is 0.0054. So minus point, I always forget to change it back to pen, 0.0554. Go ahead and do subtraction. Subtract these two areas, 0.8599 minus 0.0554 turns out to be 0.8045. 0.8045. Is that correct? 0.8045. 0.8045. And let me double check really quick. If you were to use a Casio 991 calculator, you would press on and then menu and then number 7, and there you see normal PD number 1. We need number 2, which is normal CD. My lower range here is 2.55. My upper range here is 1.08, and it turns out to be 0.85. Looks like I've messed up somewhere here. Let me go back and check my areas, okay? Let me go back and check. 1.08. 1.08 and negative 2.55. 1.08. 1.08 is 0.8599. Okay. 1.08 is 0.8599. Okay. 0.8599. And negative 2.55. Negative 2.55 is 0.0054. 0.0054, and when I subtract them, see what I get. 0.8599 minus 0.0054 turns out to be 0.8545, okay? 0.8545. 0.8545 is the area in the middle of these two z-scores. Now, I'm not going to do the rest, but I'm going to have you work them out and check and match your answer with me. For part B, I believe it should be 0.7560. For part C, I believe it's 0.7626 after you subtract them, and 0.214. So go ahead and draw these curves, find the two z-scores and subtract them. Remember, when you're looking up to a z-score, it tells you the area to the left, okay? Now we'll look at number 4, part A, okay? And we'll also look at part C as well. So for part A, number 4, we are looking for the probability or the z-score or the area to the left of negative 0.51 and also area to the right of 2.6. Now, very first thing we got to keep in mind, R means addition rule of probability. I'm going to be adding the two areas, okay? R means addition rule of probability. Negative 0.51 would be somewhere here, negative 0.51. 0 is in the middle. 0 is your mean. That's exactly in the middle. So area to the left of negative 0.51. Let's look for negative 0.51 and find the area to the left of it. That turns out to be 0.3050. So this area turns out to be 0.3050. Now I also need the area to the right of 2.6. So 2.6 will be a little bit farther. 2.6 will be a bit farther. 2.6. So all that area is what I'm looking for, and go back to the table. 2.6. Is it 2.06? No, it's 2.6. If you want to round it to two decimal places, we can call it 2.60. So look for 2.60 here. 2.60 turns out to be oh, that's the area to the left. We want the area to the right. So you can really do it in two different ways. One way, you know the distribution is symmetric. You can look at negative 2.60, or you can do 1 minus 0.9953. 1 minus 0.9953 is okay to do, which is 0.0047. So either you can do 1 minus 0.9953, which is 0.0047. That gives you area to the right because we had the right sided shaded. Or we could look negative 2.60, which is here, and that would work out for us as well. So either way, both are correct, and it's totally up to you however you want to do it. So let's go back to the notes. So this is 0.0047. Now, whenever you have or in the middle, you're going to be adding these two areas, and that means or means plus. So 0.3050 plus 0.0047. And when I add them up, it turns out to be 0.03. No, 0.3050 plus 0.0047 turns out to be 0.3097. 0.3097. Okay, turns out to be 0.3097. 0.3097. Okay, now the next one I am not going to work out, but I'm going to have you do it by yourself. So do it and check with me. It's going to turn out to be 0.8956, 0.8956. Okay, now let's look at part C here because that's slightly different. How does part C turn out to be? For part C, we are looking for the area. For part C, we want the area in between negative 1.26. So let me mark negative 1.26. That's probably here approximately. And 3.25, that is here. So we want all this area. Now, how will we find this area? First, we can find area to the left of 3.25, and then we can find the area to the left of negative 1.26 and subtract them. So how much area is to the left of 3. Let's see. Okay, I think this is, go back, this is not correct. I believe this is going to be 0.9204. So 9204. Please match and check and see if I have it correct. For part C, we are looking for both the areas and subtract. Look for the area to the left of 3.25. Well, look in the positive z-scores. 3.25 is all the way on the bottom. 3.2. And then let's see, 0.9994. Okay, that's the one we have. So this area is 0.9994, and we want to subtract. This is all the area to the left of 3.25, but we want to subtract the yellow highlighted area, which is area to the left of negative 1.26. Again, go back and look at the table. Negative 1.26. Negative 1.26 is going to leave me with .1056. Negative 1.26 leaves me with, nope, 0.1038. 0.1038 is what I am left with for negative 1.26. 0.1038. 0.1038. And if I subtract 0.9994 minus 0.1038, it turns out to be 0.8956. And that means there's 89.5% of the area in the middle of these two z-scores. A lot of area in the middle of these two z-scores. Okay, draw and shade normal curve. How would you draw and shade the top 10%? Well, the top 10% is going to be, it's going to be on the positive z-score side. Its top 10% is going to be somewhere here. It's got 0.1000 area to the right. If it's got 0.100 area to the right, how much area to the left? Well, it would have 90% area to the left. For the bottom 25%, is going to be something that has 0.2500 area to the left. If it's got 0.25 area to the left, how much area to the right? Area to the right, 25% area to the left means 75% area to the right. Now we have 75th percentile. 75th percentile means 75% of the area is below your mean. 75% of the data values are below that data value. So 75th percentile means 75% of the area is to the left. And if I change that 75 into decimal, it turns out to be 0.7500. 0.7500. Okay, cool. Next example is already worked out. I'm going to go ahead and have you take a look at it, read that example, and I'll move on to the ones that are not done. So here's the example. We're going to look at page 181. A certain bone density curve is normally distributed with a mean of 0 and standard deviation of 1. A randomly selected adult goes through the test. Find the probability that the result is less than 1.27. Okay, one thing that tells me because the mean is 0, standard deviation is 1, I'm dealing with a standard normal curve, okay? We're looking for the probability of randomly selecting somebody in a standard normal curve. The data values and the z-scores are the same. So basically, I'm looking for the probability of x less than 1.27. Remember, the data value and z-score are same for our standard normal curve. For standard normal curve, the data value and z-scores are the same. Data value and z-scores are same. Data value and z-scores are same. Okay, z is less than 1.27. So let's go ahead and draw my curve. Where is 1.27? It's approximately here, and we're looking for the area to the left of that. Okay, we're looking for area to the left of this z-score. Let's go back to the table, find out the area to the left of 1.27, and we have done enough reading of the table now. So I'm gonna use a calculator really quick and find out area to the left of 1.27, and I got 0.8980. Okay, so how would you interpret this? There's about 89.8% chances, 89.80% chances that you randomly select somebody and their bone density is less than 1.27. Okay, high chances that you will find somebody, you randomly select a person and their bone density is less than negative 1.27, or was it positive? Let's see, positive 1.27. Next, we're looking for the bone density greater than negative 1. Where is negative 1 on your standard normal curve? The negative 1, well, this is 0, and negative 1 is here. We want the area to the right of negative 1. Remember, our table does not give us area to the right. It actually gives us area to the left. So whatever I get from the table, I have to do 1 minus. Let's look for the area to the left of negative 1.00. Negative 1.00. Here it is, 0.1587. But we want the area to the right, so we have to do 1 minus 0.1587. And that turns out to be 0.8413. Okay. For the next one, ignore these symbols. I couldn't find the less than symbol on my keyboard, so I ended up using this. But they do mean, I did mean the less than here. Okay, so we want somebody with the z-score or the bone density. In this case, remember the z-score and bone densities are same. Z-score or bone densities between negative 1, so negative 1 is here, and negative 2.5. So we want this shaded region. Whenever you're looking for this shaded region, you have to find area to, so this is where your mean is. And that's just to show where the mean is. We don't need it in this problem. I'll have to find the area to the left of negative 1 and then area to the left of negative 2.5, because area to the left of negative 1 is going to be this, all this green area. Area to the left of negative 2.5 will be this pink area. And if I subtract them, I get the in-between area, which I'm going to make yellow now, although it's hard to see the color. So what I'm going to do is find the area to the left of negative 1 and find the area to the left of negative 2.5 and subtract them. To the left of negative 1.00, 0.158 now. Negative 1.00 would be 0.1587. 0.1587. Area to the left of negative 2.50. Negative 2.50 is 0.0062. 0.0062. And let's see, 0.1587 minus 0.0062 turns out to be 0.1525. So 0.1525 is the probability or the area. So probability of randomly selecting somebody who's, you should write it in complete sentence. Probability of randomly selecting an individual. Probability of randomly selecting an individual. Randomly selecting an individual with bone density between negative 2.50 and negative 1.00 is 15.25%. So, or you can say it's 0.1525. You can also express it in terms of percentage. Find the bone density score corresponding to 95th percentile. Okay, 95th percentile is, let's check it out, 95th percentile. I will be looking at 95th percentile means it's got 95% area to the left. 0.9500 area to the left. So Now we're going to look in the body of the table, 0.9500. Clear the table really quick. 0.9500 in the body of the table, 0.9500. 0.9500 is actually, we saw earlier, the 0.9500 is in between these two values. So we can take, it's in between 1.6 and 1.64 and 1.65. So I would say it's 1.645. Okay. Again, you can do the average of 1.6, 1.65 divided by 2. That's how I got 1.645, because 0.9500 was not on the table. Not on the table. This was not on the table. Not on table. It was in between value. It is exactly in the middle of other two values. If you don't find exactly in the middle, you can go to the one that's closest. In this case, it was not closer to any one of those. It was equally distant from both. Find the bone density score that separates the bottom 2.5% and the one that separates the top 2.5%. Remember, the bottom 2.5%, if I change 2.5% to a decimal, I'm looking for the z-score that has 0.02. I would move the decimal 2 places, 2.5%, 0.025 area to the left. So I have 0.025 area to the left. So find the z-score that has 0.025 area to the left. Again, you can go to the z-score table, look for 0.025, not 0.0025, but 0.025. And that looks like this is the one. Here it is, 0.025, and it's going to be negative 1.96. Negative 1.96. And because this distribution is symmetric, I already know that the other side will be also, this would be 1.96, the one that separates the top 2.5%, 0.025. Okay. And that's it for this video. This covered the standard normal distribution and uniform distribution.